Well, hello, Cal State Strub. Here we go. Chapter 13, Section 2. Before we jump into two sample testing for proportions, I want to spend a little bit of time here making sure we are solid on two sample testing for means as a review. Okay. If you have not yet printed out the worksheet that goes with today's notes, please pause, go do so. That worksheet is going to be crucial to today's lesson. It is the best review sheet and the best thing to have handy during the AP test since you get to use notes this year. So have that out there. Go take care of that and come back and be ready to review. All right. If we're ready to go, I have a quick warm up here for us to take a look at to review two sample t-tests from previous notes this chapter. So the SRS of 50 college students were asked how many hours of sleep they get a night, and you get those answers there. Another SRS of 40 high school students were asked the same question. Remember, your N doesn't have to be the same size for the two samples. Okay. The high school students' information is there, and it asks you to do a significance test to see if there's evidence of a difference in the average amount of sleep high school students and college students get each night. Assume all the conditions are met and use alpha at 0.05. So you don't need to run the conditions here because it tells you they're all met. Remember, we've talked about this like in an AP test. Don't answer too much. So if it says assume all conditions are met, then just say census conditions are met. Okay. You could make a mistake in trying to prove them and then they'll mark you off for it. So go ahead and give that a shot and come up with your conclusion to put into Edpuzzle, and we'll come back and look at the answers. All right. Your two means should have been stated, and that includes my proportion, my parameter and my population are in those. I labeled them C and H for college and high school. You could label them 1 and 2. We talked during the last section about just labeling them so you understand what's going on. There's your ho and your ha. This is a two sample t-test because they're two distinct populations and separate SRSs from each. We did not get a direction for this, so this is a two-tailed test as well, the not equal to. I ran through the formula method there and got the answer you could compare to yours. Since DF was 39, we went up the table to the 30 and saw what T was between because it's two-tailed, remembering 2 times that p-value by 2. So we are definitely less than 0.05 there. So it is statistically significant evidence at that level to reject HO and conclude that the number of hours of sleep is different for these two groups. Okay. When I ran this through the calculator, it gave me 0.01329. So if you ran the calculator command, that's probably what you got instead. Remember that you have to divvy that p-value into half on your sketch. So here was our t. The way we did this was negative 1.2 here. All right. And our SE is 0.4748, this formula here in the denominator. That even if you do your calculator command, you must go do the math for that. Okay, and so you're going to mark that off until you get to the 1.2, negative 1.2, which would be about, that's like almost 3 standard deviations away from the mean difference is 0 here, saying there's no difference between them. And then go the opposite side of that. If you got a negative 1.2 here, then this is 1.2. If you had gotten a 1.2 as your difference between the means, then you would come here and do the opposite. So making sure that you surround that 0 symmetrically. And then the p-value that I got of 0.01329 was cut into half for each section. I just did the conditions. It said to assume, if you had to show them, just a reminder what you would do, that you have to say given for both, CLT for both, and then independence for both, and then independent of each other. Just a reminder, that's the added thing that you have to do, that that high school and college students, we're assuming, are independent of each other. We do realize there are some students in high school that are taking college courses, but they would have to declare either or for this situation. All right, we're going to go now to the worksheet. Oops, if I can get it to go there. That I asked you to have ready. This is huge. I think that this kind of a question will be what you see on the test, since they are going to be using Minitab. I just can't, I imagine things like this are going to show up since they're not making you draw or do heavy calculator commands. So this is a very interesting test. And to see if breastfeeding weakens bones, because there's calcium that mothers that are breastfeeding do secrete into the milk. So it just says here, some of the calcium may come from their bones, so mothers may lose bone mineral. Researchers compared a sample of 47 breastfeeding women with a random sample of 22 women of the similar age who were neither pregnant nor lactating. And they measured the percent change in bone mineral content, that's the BMC here, of their spines over 3 months. So comparative box plots and summary statistics for the data are shown here using Minitab, and it asks you to answer, is the mean change in BMC significantly lower for the mothers who are breastfeeding? Carry out an appropriate test. Okay, obviously, guys, this is 2 separate populations, breastfeeding or not. You can't be doing both. Okay, so it's 2 sample t-test here because we're comparing the means. Now you can look at the box plots and see what they got there, but come over to this chart and you will be able to tell. It tells you here what these 3 values are in the Minitab plot. So you get your means for each here, and then your count. So this right here is your breastfeeding, your non-breastfeeding, or non-pregnant, non-breastfeeding. And then the standard deviation, the S for that sample. So there's your data. I would highly recommend using your calculator command, but remember you have to list what it is you're putting in. Okay, so if you will go through that, and then question C asks you, can you then conclude that breastfeeding causes a mother's bones to weaken? Why or why not? So answer that question. And then part D asks you to now construct and interpret a 95% CI for the difference in means. Okay, this is a total review of exactly what we've been learning for 2 samples. I'm almost certain you're going to see a 2 sample test, probably a 2 sample t-test, or a paired t. I just think they're going to do one or the other on this test. We just all have this feeling. We might be wrong, but we have a feeling. Okay, so construct that and then explain how that interval compares to the significance test the answer that we got. It says part B, but this is actually right here what it's referring to, your significance test, okay? And then the final thing this worksheet asks you to do is to determine if these are paired or unpaired procedures. So it says tell whether you should use paired T or 2 sample T, and explain why you chose what you did. So you're going to need to pause here, go into some work mode on your own, and then put your answers into Edpuzzle, and then we'll come back and check together. All right, that was probably a bit of work that you had to do on your own. I'm just going to put up some answers here for you to compare what you did. The difference being 0. And then I did put, this was a directional one that breastfeeding minus non, I used N for non-breastfeeding, non-pregnant there. Okay, make sure that you've labeled everything carefully. SRS was given for both independence and CLT was met for one, but CLT was not met for the other. But they gave you a box plot. You don't need to go do a probability plot. You just look at the box plot. And when you take a look at that box plot there for that smaller one, you see that it is right here fairly symmetrical. So we can go ahead and assume it's approximately normal. Okay. So that's where that came from there. Here's all my data from one of our stats, from the stats above, actually, that they gave us. And I plugged it into the formula, used my table. It went off the table. Remember, when it goes off to the right, then that means p-value is less than the last thing off on the chart, because the p-values are getting smaller as you go to the right. So that's super tiny. If you did it on the calculator and you did stats, not data, because you don't have the data, you use the stats that were given to you, and you ran a 2-sample t-test and said, look what you got. Look at this. Super, 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 super small. And this was the DF that came up. Remember, if you do your calculator commands, you put all of the input and then the output, and you got these things on output. I was just highlighting the difference there because I'd done it by hand. So we have a teeny, 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 tiny p-value. So we have extremely strong evidence against the Ho. We're going to reject it and say there is significant evidence that the mean change in the bone mass content, sorry about that, is lower for mothers who are breastfeeding. So there we go. There's less than a 0.0005 probability of getting a mean difference that we did just by chance. Remember that that's what this means when we are looking at our p-value. Okay, your sketch there, your SE is 0.458, so we're just way off on the left with that negative 389 difference way out here, teeny tiny. Okay? So then I hope you thought through the next part. Can we conclude that it causes it? Remember, this was not an experiment. This was an observational study. Again, this is probably a great question that they will use on, and this is so much like what you could see, because it's comparing things from the past units. And that one thing is we can't say causation unless we have conducted an experiment. This was observational, okay? So we cannot say it causes it. We could only say that there is a difference and that we have strong evidence that there is a difference. But that doesn't mean it was the breastfeeding that caused it. We would then need to go run an experiment to check that. Okay, here's your 95% CI. I did it by hand. Again, you can run a 2-samp T int on your calculator and get the values. So I did this by hand here and then also by calculator, and you could see very similar situations here, but we're 95% confident the mean bone loss is between these two percentage values. So what this does is this gives us more information now. We noted in the significance test that there was a difference. How much of a difference is there? And we could see that. Also, we see that 0 is not in this interval, which is why we rejected the Ho, that there was no difference from the previous test as well. Okay, so this is nice. We run a test and say, wow, there is a difference. Now let's go see on average, how much is that going to be? And there's your percentages that you got. Okay, hopefully you thought through these. I'm just going to put up the answers for you to check. This one was a paired T because it was the same subjects getting both treatments. And the remaining 2 were 2-sample Ts because they were 2 distinct groups. If you have any questions on that, bring it to the next conference session. Phew. All right, now into today's notes for comparing 2 proportions. Okay, we just now went through a lot on the means. What about proportions? Proportions have a couple really interesting things that get added to it. Right? Our Hos and our Ha's are going to be exactly how we set them up for the means. It's just going to be P's now, because remember, we're doing proportions. So either your proportion, you set it up like this, that they are equal, no difference, or you could say when I subtract them, I get 0 because there's no difference. And then it's either right-tailed or left-tailed. tailed, the differences being greater than 0 or less than 0. Okay? Or two-tailed, where you would say not equal to. Your sketch, right here, I've got a sample of your sketch. In the center is going to be the subtraction of your P1 minus P2. That will be, oh dear, goodness. Most of the time that is 0 for us because we're saying that there's no difference between the proportions. Only this would not be 0 here. This subtraction of the p's would not be 0 if the problem says that it is known that the difference in the proportions is 10%. Then you would be using 0.10 there, okay? All right, so we have the 0 here, the difference. This is your, I do not know why this keeps doing this. This is your standard deviation formula here, okay, that you would be using. We've already done this formula, half of it right here in all of our other proportion testing. Now that we have 2 samples, you're adding that formula for each underneath the square root. Okay, we're going to talk about that in a minute. So this is your sampling distribution that you create the sketch for, your difference of the 2 p-values, or not p-values, 2 proportions in the center, which is usually 0. Then your p-hats, your estimates that you got from your samples, subtract those 2 and put that on your chart and put your p-value there. Okay. All right, now let's just go to confidence intervals if you have 2 samples. Just like the means, instead of putting just p-hat here, the subtraction, the difference of the 2 p-hats goes here. And we go back to our z-star for proportion, just like we did for 1 sample. And then here is our formula now. We're using p-hat 1 and p-hat 2 inside that. Again, it looks just like before, only we've got to add the second one in. This is called a 2-proportion z-interval. You still check conditions, but remember you're checking for both to be random. Here's the slight change. You're going to use n1 p-hat 1 and n1 times 1 minus p-hat 1, and then you go to n2, so on. It's written there. And it will be okay to be normal, to assume it's approximately normal, as long as all these values are at least 5. In the past, it's been 10, but because we're combining 2 sets here, it actually does work out as long as they're at least 5 in each of those calculations. You still do your independence condition, but for both. And then I just put here, note the slight difference here than with our other tests was that 5. Okay. Now, significance test is where it gets a little bit different. For a significance testing, in the 2-sample mean testing, we used the where am I trying? Sorry about this, guys. We use the X bars, and you're using those inside your formula, and then but when we did 1 sample p test, proportion test, there we go. 1 sample proportion test. When we were doing that, we got that. Oh boy, I'm gonna have to cut this part out. Okay, when we do 1 sample proportion test, okay, we use the p null in our formula. We use p-hat in confidence intervals and p null in the formula. Okay, now that we're doing 2 samples, we just showed that we use the p-hats inside the formula, but we use something called a combined sample proportion now for the testing. We don't use p null. Okay, we're going to be using p combined. Okay, so our combined p-hat is this is the notation for it. P-hat sub c is where you add up the successes from both samples and divide it by the total n's together, n1 plus n2, and you come up with your combined p-hat. Okay, and now your test statistic for this is going to be still the same. we're subtracting 0 over here because our P1 minus P2 is most of the time 0. If it was different, then you'd put minus P1 minus in parentheses the P1 minus P2. But notice our denominator looks really a little different, okay? This is because we're not using P hat 1 and P hat 2 anymore. We're using this P hat combined. And if you distribute these to this, you would see that this would be the numerator of each. So it looks exactly like the previous formula we showed. Let me go back to it here, except for because these numerators are now the same, you can factor that out and you're left with 1 over n1 and 1 over n2, like that. Conditions, same thing, SRS for both. Normality now, we still use the N1 P hats, C's now. So instead of using the P hat 1 and P hat 2, you're using this combined proportion, this P hat C, okay? So we use that in normality, and actually it still will work as long as they are 5. But most of the time they're always greater than 10 like they were before. So if it goes in greater than 5, then you don't need to say proceed with caution. Independence for both, same condition. Okay, so here's the deal. This combined proportion is only used to test. It's not used in the confidence intervals. The combined proportion is used to check normality and in the formula. Okay, so those are the two places that you'll be doing this when you do 2 sample proportion testing. So let's do an example here to close out this and make sure we can run through this. So we're going to do a test and a confidence interval, okay? So let's start with a confidence interval. Gave you some data here. We got some East Coast versus West Coast. This was made up data, so this is not true data. But anyhow, this people who plan to vote for Trump, okay? So you create a 2 proportion confidence interval at the 95% level. And so I needed to get my 2 P hats calculated for the East and the West. Okay. Let's make our hoes and our haws coming up. So the hoe is that they are, by the way, we don't do a hoe and haw for confidence interval. I'm just getting us all set up to think through this. Okay. Sorry about that. The hoe is that they're equal. The haw is that they're not equal to, and all conditions checked. Okay. So let's run through the CI first. Here's your difference of your P hats, plus or minus your Z star for 95%. And then here is your P hat 1, 1 minus P hat 1, P hat 2, 1 minus P hat 2, and then your N1 and N2. Calculating that formula, I got this information that I am 95% confident that the difference is between here and here. As we could see, 0 is in this confidence interval. So we cannot reject HO, that we'd have to assume that there is no difference, that the East Coast and the West Coast would be voting differently doing the CI method. Now let's go to the testing method. We're on a significance test. Okay. Now this time, let's just say we're saying we think the East Coast has a higher proportion than the West Coast. So again, I'm just going through conditions have checked. Remember to use P hat C in your conditions here, not P hat 1 and 2. Here's our combined P hat C, adding the 2 values. Okay, we had 175 out of 500, 120 out of 400. So that gave us this 295 out of 900. There's our P hat C. So I have the P hat subtracted here. Our hypothesized difference was 0, so it's not there. And then here is your P hat C, 1 minus P hat C, and then 1 over N1, 1 over N2, calculating to this Z statistic, which goes on the table to be that. We are doing a right-tailed test, so we need to subtract that from 1, and we get this p-value. So again, there's not enough evidence at the 0.05 to reject the hoe, so we conclude that there is no difference between the East and the West Coast, how they will vote for Trump. Okay, so I've got an example there of a CI for you and a significance testing. You're going to try a couple homework questions, and tomorrow's notes, I will come back, do some calculator commands with you first, and do some practice on this. But try to practice it up and bring your questions to conferencing time. We'll see you on the next video. Oh, I forgot. Before I go, I really wanted you to see that this is all on your formula sheet before you freak out too much, just like the means were. Here's your 1 sample testing. Here's your 2 sample testing. And they do tell you about using p-hat-c. This was never on the old formula sheets. This is new this year. I'm so glad they did this for us. So it reminds you here to use that p-hat-c. You have to know to use p-hat-c for testing and not for the interval. So that's the knowledge you have to bring to this, but the formulas themselves sit here. All righty. If I can find my, there we go, get out. All right. It's not letting me out.